In this video, we'll talk about hemoglobin. Hemoglobin is an enzyme whose primary job is to bind and carry around oxygen for the good of the body. Oxygen binds in the active sites of hemoglobin. Since hemoglobin is a 4-subunit molecule, each hemoglobin can carry 4 oxygens. But amazingly, when an oxygen binds to a hemoglobin molecule, the affinity of all of the other subunits for oxygen increases. So once it's bound 1 oxygen, it will be more likely to bind the next oxygen. And if it's bound 2 oxygen, it'll be more likely still to bind a 3rd oxygen. Okay, so this shape change that is caused by the binding of oxygen to subunits of the hemoglobin molecule is called cooperativity. The kinetics of cooperativity create a sigmoidal shape when you do a curve with the same axes as a Michaelis-Menten curve. So this is oxygen concentration on the x-axis. This is oxygen saturation on the y-axis. So it's a little different than an enzyme. You're not making product. Instead, you measure what percentage of the hemoglobin is filled up with oxygen. So this graph only makes sense if you think about a population of hemoglobin molecules, not a single molecule. A population of hemoglobin molecules will have more of those molecules with an oxygen bound to them as you increase the quantity of oxygen in the media. Another increase in oxygen and you get in higher affinity, higher affinity, higher affinity. This is because of the increased number of already 1 or more bound hemoglobin molecules as you get more and more oxygen in the vicinity of those hemoglobin molecules. So that's the meaning of cooperative binding. The advantage of cooperative binding is that the affinity change of hemoglobin is advantageous both when you're trying to bind oxygen so that you can bring it back from the lungs. This high oxygen concentration is what you'll see in the lungs. So you want to bind as much as you can. And then you want to let go of oxygen when your tissues need oxygen. So where oxygen is not available to tissues, then it's not going to be very concentrated in the blood. Therefore, hemoglobin lets go of oxygen there at the low oxygen levels. It's doing a great job. If it was instead insisting on holding on to that oxygen, if it had a higher affinity, then it wouldn't be doing the drop-off part of that delivery job. Okay, so that increase in affinity leads to oxygen binding, where oxygen is going to be picked up, and letting go of oxygen where it's needed. So you'll notice that exercising tissues are going to deplete local oxygen concentration enough so that 80% of the hemoglobin's oxygen content is going to be unloaded. Whereas in resting tissues, it'll only get rid of about 50%. So there's more oxygen left over. It's not dropped off where it's not needed, but it is dropped off where it is needed. To illustrate why this is a better situation than if hemoglobin was always in its higher affinity state, let me show you the picture the book provides us of non-cooperative binding. So this is specifically non-cooperative binding with the hemoglobin molecule locked into a high affinity state. And so you'll notice that if the low oxygen concentration associated with heavily exercising tissues, the unload would only be 50%. And so much more oxygen is actually dropped off in a cooperative kinetics situation than would be if there was an always high affinity state to this hemoglobin. Show you another graph in which the affinity of hemoglobin in mom is compared to the affinity of hemoglobin of the baby. So the baby will grab oxygen from its mother, be able to outcompete the maternal hemoglobin for available oxygen. Now, if we get rid of these titles, this looks an awful lot like another graph in which you have a relatively high pH environment compared to a relatively low pH environment. And if you see a graph that has those labels, then it's probably going to also be labeled a graph of the Bohr shift, because the Bohr shift represents the effect that carbon dioxide and protons have on the affinity of oxygen for hemoglobin. So those are equivalent. This, therefore, is an allosteric relationship. It's allosteric because both carbon dioxide and protons are binding to a site that is not the active site. Therefore, it's not direct inhibition. It's allosteric, it's binding somewhere else, and it's changing the Km, although you can't actually call it Km unless you have a straight line here, so it's not officially a Km. But nonetheless, the affinity changes, the Vmax doesn't. So that's an allosteric relationship. The amazing thing is that if you were to turn this around and look at the affinity of hemoglobin for carbon dioxide and protons, you'd find that oxygen is an allosteric inhibitor of the binding of those two molecules. So what we think of as the active site becomes an allosteric site if what you are measuring is the binding capacity to protons and carbon dioxide. The last thing I'll tell you, I've told you in lecture, that I'll tell you about hemoglobin is that it also binds or makes or has some relationship with nitric oxide, and it releases nitric oxide when oxygen levels get very low. So when it drops off its oxygen, and oxygen levels seem very depleted around it, so maybe that means that most of the hemoglobins are empty, that's when it lets go of nitric oxide. And when it lets go of nitric oxide, that nitric oxide acts as a local signal telling the muscles in the blood vessels to loosen up, to allow more blood flow. So, what is hemoglobin doing? It's carrying away carbon dioxide and protons from active tissue and bringing them to the lungs where the carbon dioxide can be respired, and the protons can be reunited with bicarbonate to make the carbon dioxide and water. And again, that carbon dioxide can be respired. Now, what did I want to say in addition to that? I forget.